All right, welcome back. So we are looking at section 3.1, which is Introduction to Determinants. So the question that you might have, which is valid and reasonable, is how would we find determinants when we have like bigger matrices? Because when you're looking at determinants, right, you're looking at like for a 2x2 for the A, B, C, D case, right? The determinant here, which I'm gonna just make this notation. That's just multiply here, so AD, and then subtract BC. BC, right? But what if we had like a 3x3? Well, that is an excellent question. If we're looking for bigger than 2x2, our determinant of our square matrix A is the sum of some terms, and these terms are going across our row, and then multiplying by like a submatrix determinant. So if, for example, you had this matrix A, B, C, D, E, F, G, H, I, then you would find, in order to find the determinant here, you would take A and multiply it by the determinant of your submatrix, defined by taking away the first row in the first column. So you're getting a submatrix, which is now a 2x2, so now we can use what we had before of EI minus FH. And then subtract now, so we're subtracting our A sub 1, 2, which is here, this B. So this is B times our submatrix A sub 1, 2's determinant, so that's D, F, G, I. So the determinant there is DI minus FG, and then, let's get one more thing. So then we also need to alternate, so we're getting plus with this C, and then the submatrix. This is determinant, which is C times DH minus EG. So that's like our 3x3 case, but you can also do that for bigger matrices. You just need to do that again, because like if you had a 4x4, for example, you would need to break it down into 3x3s, and then from the 3x3s, you need to break it down to 2x2s, and then use the multiply, subtract, multiply thing. So that is a lot to like kind of do, but that's okay. And we also have a name for this like alternating determinant of our submatrix A sub ij, and that is called our cofactor. So cofactor expansion, or using cofactors is going to come up. So that's our vocab. We've got cofactors right there. How would we compute the determinant of this matrix, which is a 3x3, but we also conveniently have some zeros. So that'll be nice, right? Because 0 times anything is going to give us 0. So well, we can just go through, we can go across. That is one option. So we can have 1 times, so our determinant of A is 1 times 4 times 0 minus negative 1 times negative 2. And then we have minus 5, right, because we have our alternating. So this is now going to have an odd power on our negative 1, because this is 1 plus 2. So we have 5 times 2 times 0 minus negative 1 times 0. And then we have 0, which is just going to give us plus 0 times whatever. It doesn't matter because it's 0. And that simplifies nicely. We get 1 times negative 2 minus, that's 0 and that's 0. So 5 times 0 is 0. So we get this equals negative 2. So our determinant for A is negative 2. And that's non-zero, so that's nice, right? Because then that tells us that our matrix A is invertible. that factors would come up again. So our determinant of our n by n matrix A can be computed by a cofactor expansion across any row and down any column. So we don't just have to be we don't have to go across our first row if another row is more convenient. And just thinking about that and what we had before in this problem, was it most convenient to go across this first row? Maybe not, right? Because we ended up with having zeros. And so it might have been better to go either down this last column or across this last row, where we end up with really only doing our one multiplication with this like -2 times 1 times -1 minus 2 times 0, and then everything else would zero out. That would be nice, or doing it with zeros and then this -1 with the 1 times -2 minus 5 times 0, and then the 0 again. So, you know, it could be better to use any row that isn't the first one, which is pretty nearly what happens in this case, where we have rows and columns that have more zeros than non-zero entries. We would probably choose those in order to compute our determinant. So, with that in mind, let's continue reading. So, our expansion across the ith row using the cofactors is determinant of A is equal to our A sub I1 times our cofactor, which is that -1 to the I plus j, so this would be I plus 1 power, times our determinant of the submatrix. And then we just parse through the rest of the row. Or we could go down the jth column, just parsing through, keeping our row, indexing our row up, but keeping our column the same. So we have this lovely pattern, this checkerboard pattern of pluses and minuses, because the parity changes with each of these locations on what -1 is going to be raised to. And so that's quite lovely. And just notation-wise, if you're thinking about like LaTeX stuff, then this ... I'm always too lazy to actually remember what it is, but this diagonal dot is \d dots. And then this vertical dots, this one, is \v dots, I believe. So you might see that in the next problem set. If we're using our cofactor expansion across the third row to compute the determinant of A, where we have the same matrix A, then we get determinant of A is equal to, we got a 0 for our first thing, minus -2 times our determinant of this, which is -1 minus 0, and then plus a 0. So -1 minus 0 is -1, -2 times, -2 is +2, so we end up with -2. It's the same determinant, which is pretty cool. And there's also another way of looking at this. Let me try to see if I can make this bigger. Okay. So our expansion of a 3x3 determinant, we can also remember by kind of doing it this way, which might work for you if, like, juggling all of the submatrices is a little complicated. This is how I like to remember it. But this only works for 3x3s. It doesn't work for bigger matrices. So, because, like, maybe you can journal about why. It's cool. So, we have our matrix A, that's here. But then we're going to like fake augment it with repeating our column 1 here, and then repeating our column 2 here. And then what you can do, since what you're doing is like multiplying and subtracting, what you can do is just multiply the product of this diagonal plus the product of this diagonal plus the product of this diagonal, and then subtract out the product of this diagonal minus this diagonal minus this diagonal. So you're effectively doing all of the same operations. It's just kind of regrouped. And so this might be another way that you might want to do it. This is it's kind of elegant. It's pretty cool. And so if you're thinking about this, then it also makes it a little bit clearer about what happens with triangular matrices, which we're going to look at soon. But if you suppose you had this like 3x3 and you were looking for its determinant, and it happened to be also upper triangular. So that means that what would we have? We would have zeros here, here, and here, which means we would have zeros here, here, and here. So what happens? Well, a lot of things get zeroed out, right? So the only thing actually that doesn't get zeroed out is this one diagonal. So think about that, and we will come around to it again. Compute this determinant of A, where we have this almost upper triangular matrix. Bummer. It's almost upper triangular, but it's not quite. So what are we going to get? Well, it actually seems like either column 1 or row 5 would be optimal for us to deal with. And since, I just kind of don't feel like going across here, we'll just try for going down here. So we have the determinant of A is going to give us 3 times the determinant of this matrix, which I guess I'm going to write with the this notation. I will not bore you when I write this. We get 3 times this, and then like minus 0 plus 0 minus 0 minus plus, and then plus another 0, which all doesn't matter, right? And so we can do this again using our first row again, and what do we get? I'm going to erase these guys. We get 3 times 2 times our determinants of our submatrix here, and then plus and minus plus minus zeros. So I will write that down. And now, well, actually, this looks pretty familiar, right? That this is what we were looking at before, where we have the matrix that we were using before. Let's use this last column. So our determinant here is going to be 0 minus, let's do 3 times 2 times our determinant of this 3 by 3, which gives us negative 1, so that's positive 1 times negative 2 minus 0. We get zeros everywhere else. So that ends up with 3 times 2 times negative 2, which is negative 12. So our determinant for that 5 by 5 matrix A is negative 12. If we have our triangular matrix A, then our determinant of the product, the determinant of that matrix A is the product of all the entries on the main diagonal. So if you are thinking about like some matrix where you got like stuff down your diagonal, you got another thing, you have like stars and hearts and smiley faces here, so you get non-zero entries up here, but you got all zeros down here. Then your determinant is going to be the product of all of those, because the 0 is going to zero out everything else pretty much, right, when you're doing that computation with the cofactors. And the same thing works if you are looking at matrix that is got zeros on the upper part of the triangle, and then you have like other things here. So this 0, all these zeros are going to zero out everything else, and so all you're going to be left with is the product of what's on your main diagonal, which is nice. It's nice to be able to have things like that, because with our we do also know how to make triangular matrices, right? With our LU factorization, that we can take a matrix and then break it up into upper and lower triangular pieces, and then those we can use very nicely with our determinant, because then we can just find the determinants of those two matrices separately. And I wonder how those relate to one another. We will find out. All right. So what did we learn? Determinants. There's some patterns that we can follow to compute determinants. There's a lovely kind of like grid thing we can do, but it only works with 3 by 3s. And you are not limited to going like across a row or anything like that. You can use any of the rows or columns when you are figuring out your determinant using your cofactor expansion. Just make sure that you keep in mind the pluses and minuses. That's the key. All right. See ya.